Thank you very much for attending this morning, afternoon, depending on where you are in the world. The title of the talk is Small Angle Neutron Scattering Instrumentation Opportunities at Oak Ridge National Lab. And I will start with a very brief introduction, because I didn't know necessarily who was going to be in the audience. I assumed that there would be a lot of people who spend a lot of time at synchrotron facilities and are not necessarily familiar with neutron scattering techniques. So, let's see if this works. Here we go. All right, so I will start with the really basic stuff. The neutron is a subatomic particle. It has mass, no charge, and it has spin. And its interaction is primarily with the atomic nuclei. All of these things are really important. It makes it a very useful probe, much like X-rays are. So when you are thinking about the wavelength of a neutron, it's directly related to the speed of the neutron. The faster the neutron is going, the shorter the wavelength is. And for example, a 1.8 angstrom neutron has a kinetic energy of 25 millielectron volts, going along at about 2,200 meters per second. Now, 25 millielectron volts is obviously very small compared to your typical X-ray energy that you use for scattering experiments. Copper K alpha being about 8.1 kiloelectron volts. So when we're talking about the wavelengths that we use on the SANS here at Oak Ridge National Laboratory, we go from roughly 2 angstroms to about 25 angstroms. In terms of capability, that's kind of what the sources provide. The reason that neutrons have some interesting benefits, or it really comes down to some basic things that are related to fundamental properties. They're highly penetrating, right? So not being a charged particle means that they will penetrate most materials quite effectively. That means that you can use very complex and robust sample environments, and many of which are not necessarily suitable for X-rays. And you can study samples that may not be suitable for X-rays due to the penetrating power of it. Now, one of the features that makes neutrons of interest to the condensed matter physics community is the fact that it has a spin, because it makes it an excellent probe of magnetic materials. And we can polarize a neutron beam and improve the utility of that for studying these magnetic materials. But most importantly, the reason why neutrons are useful for characterizing materials is that the interaction is with the nucleus of an atom. And as a result, it means that neutrons are sensitive to isotopic content. A hydrogen atom does not look the same to a neutron as a deuterium atom, even though chemically they're very similar, they're the same. Chemically, you get into questions about the difference in mass having effects on things like vibrational energies and such. And yet, when you're interacting with an X-ray, clearly a hydrogen atom and a deuterium atom look the same. Now, the other thing that's really important to know about neutrons, for those of you who aren't familiar with them, is that because the interaction is with the nucleus, that's a good thing. It's an interesting thing. It gives you some unique utilities. However, importantly, the strength of the interaction between a neutron and a nucleus is comparable across the entire periodic table. That means that neutrons are very sensitive to light elements in a way that X-rays are not necessarily sensitive. And there are also some elements, isotopes, that have a negative scattering length. That allows you to do very creative things when it comes to labeling materials. So the table shown over here on the right, hydrogen has got a negative scattering length, about 3.7. Deuterium looks an awful lot like carbon. So deuterium and carbon have got a scattering length of about 6.67. Carbon-13 is a little bit different from carbon-12. Manganese and titanium are other ones that have negative scattering lengths. But if you look at uranium-238, it's not that dramatically different from the other elements that are shown in this table. Obviously, in contrast, if you're trying to use X-ray scattering to study the locations of hydrogen in a material that contains a lot of uranium, you're going to have a very hard time resolving where the hydrogen is. You're mostly seeing the uranium. It certainly is a challenge that we often experience when we're doing diffraction studies. So hopefully that gives you an idea for those of you who aren't really familiar. You use neutrons to get complementary information to what you can get with X-ray scattering, and you get unique and different information just because the nature of the interaction is different. So Oak Ridge National Laboratory is home to 2 neutron sources. The first that I'm going to talk about is a Spallation Neutron Source. The SNS, this first went live and produced neutrons in 2006, and it is an accelerator-driven facility. shown here in the figure on the left. I don't know if you can see my mouse or not, but sorry, the figure on the right. So towards the top of the image is the linear accelerator that starts the proton beam headed towards the target. The target facility, target building is shown off in the sort of upper right quadrant, just below the water tower there. There's also an accumulator ring in which these protons zoom around in a loop and they get bunched into nice little tight bundles. And 60 times a second, that pulse gets spat out into the mercury target. The interaction of the proton beam with the mercury target causes neutrons to spall off from the nuclei in the target, from the mercury. Those beams then are what gets transported out through the moderator systems and into the beams that go to the various beam lines around the facility. At the moment, we've got 19 instruments that provide a wide variety of scientific techniques. Now, this particular facility, the SNS, employs time of flight methods because it's a spallation source. So you have the ability, because you deliver a pulse of protons 60 times a second, to say, my neutrons, you generate a pulse of neutrons, they travel out from the source. Because of their velocities, you get a distribution of velocities. That velocity then spreads those neutrons out in time as they travel down your instrument. You use choppers to select the band of neutrons that you want based on their speed. And then you record the time of flight at your detector. And that allows you to perform your measurements. We have, at the moment, 19 instruments. Like I said, one is currently under construction. That's the Venus Neutron Imaging Instrument. And we have room for a few more instruments. So in this picture, you see the SNS Central Laboratory and Office Facility. The Center for Nanophase Materials Science, the Nanoscience Center here at Oak Ridge National Laboratory, is also shown in this picture. They are co-located, which is a really interesting and convenient thing to have. So the other facility here at Oak Ridge National Laboratory is the High Flux Isotope Reactor. The HFIR is a much older facility. It was first went critical in 1965. To put that into reference, I first went critical in 1970. So it is an older facility. It is a research reactor, not a power generating reactor. Its primary purpose initially was production of isotopes for research and medicine. It is one of the highest flux research reactors in the world. And at the moment, it has 13 instruments that also serve a wide variety of techniques. These instruments generally use steady state beams because that's what the HFIR excels at. It doesn't have a pulse source structure. You are essentially on all the time. We are in the midst of some upgrades of these two facilities, and I will talk a little bit about that and what it impacts in terms of operational schedules and availability. At the moment, the HFIR is planning for expansion to the cold guide hall that will include some additional instruments and some moving of some instruments. And so this is tied to the beryllium reflector replacement, which is a central element of the core of the reactor that has to be replaced on a regular basis. At the end of the talk, I will come back and discuss the plans and the future schedules and outages. SNS is also undergoing an upgrade right now called the proton power upgrade that is going to improve the flux of the instruments because it's increasing the power coming off of the accelerator from 1.4 megawatts to 2 megawatts. This is in preparation for the development of the second target station here at SNS, which will be located right next to the first target station. That is currently being developed. So we don't have money to dig yet, but we do have money for doing development of the instruments and the facilities and such. So I'm happy to answer some questions about that later. All right, so it's important to note that the SNS and HFIR are both supported by the basic energy sciences of DOE. And their mission is to serve the scientific community. So this is an important thing. These are open access user facilities. Anybody who wants to come and use the beams can do so. It's very similar to the model at the synchrotrons. There is one exception to the DOE BES support, which is the DOE Office of Biological and Environmental Research supports the Center for Structural Molecular Biology. They're responsible for operating the Biosens and the Biodeuteration Laboratory. So Biosens is at HFIR, and I'll talk about that in a bit. The Biodeuteration Laboratory is up here at SNS. these are facilities that DOE BER supports as user facilities. So this is probably a little bit different model than some people might be used to, working at the various synchrotrons where they have the CAT model at APS, or where other organizations support beamlines around the facility. At the moment, we only have one instrument that's supported by somebody other than DOE BES. We recently brought in the Spin Echo instrument, which is another one in my group that I will not talk about. That was actually built by the Jülich Center for Neutron Scattering out of Germany. And that has recently transitioned to being an ORNL instrument at this point. So we are down to one instrument that is not supported by DOE BES. And you can always get more information about the user program, about some of these instruments and facilities at neutrons.ornl.gov. I encourage you to go visit that. And that address will be mentioned a few times during this talk. Okay, so to get access to these facilities, one submits a proposal. And there are general users proposals. We have 2 calls for the general user proposals per year. These proposals are going to be reviewed by your peers. In fact, I'm guessing that I have quite a few members of the SANS panel on this particular call at the moment. For general user proposals, I want to be clear that instrument scientists do not need to be members of your team. Anyone can submit a proposal. We also accept industrial proposals as part of those calls. We have a couple other mechanisms as well for external users getting access to beam time, one of which is a proof of principle proposal. So you can submit these at any time outside of the spring and fall call that we have here at Oak Ridge National Lab. These are for test experiments. They're reviewed internally. You get up to 1 day of beam time. And again, instrument scientists do not need to be a member of these teams. That gives you the opportunity to try something out if you're preparing for a proposal, or if you really aren't sure whether it will work at all. And we do have availability of these proof of principle experiments throughout the cycle. I will also note that the EEQ Sans instrument has a mail-in program that anyone can get access to. It has some restrictions on it, and if you go to the EEQ Sans instrument page at neutron.ornl.gov, you can get more information on the mail-in program. Those are intended for measurements of less than a day, a limited number of samples, a limited number of sample environments, conditions that can be measured. The goal is to provide someone with the opportunity to have access to the instruments for some simple measurements without them having to get on a plane and come here. We are happy to have you come here. It would be great when COVID is over. We would love to have more of you here, but we're working towards that. You can also submit proposals to the Biodeuteration Lab of the CSMB. And that's usually tied to a neutron scattering proposal. So they don't want to be preparing deuterated proteins that you're going to go take off and do NMR on. The intent is for neutron scattering. But they have some very highly qualified people, experts at producing deuterated material, to work with you to help you realize your neutron scattering experiment. There are some other proposal types that I'm not mentioning here directly. So Oak Ridge National Laboratory has discretionary time proposals, and you could reach out to an instrument scientist to talk about developing a collaboration to maybe get access to some of this discretionary time. This is a good way for people to build collaborations. There's also something called a collaborative development proposal, which I did not mention here. Collaborative development proposals are intended to help you develop things like sample environment capabilities that are brand new to both you and the facility, where it is integral to doing your research with neutrons. So these mechanisms are available, and you can get more information about them at neutrons.ornl.gov. But most people will come in through the general user proposals. And we're certainly happy to receive your proposals. And the instrument staff are always willing to help you develop these proposals if you have any questions. So feel free to reach out to the staff. Okay. So I'm going to basically give an overview of the instruments we have here, and I probably am barreling along pretty quickly. So the first instrument I'm going to talk about is the GP SANS instrument at HFIR. It's on cold guide number 2. So if one looks at the photograph of HFIR, here we are. The cold guide hall, so HFIR is right smack in the center of this thing. The cold guide hall is a building that seems to come off at an odd angle from that building. Was constructed as part of the effort that resulted in the development of the GP Sans and the Biosens. They put some other instruments in the hall at that time. Okay. The instrument team consists of Lisa DeBeer-Schmidt. She is a person who's really interested in quantum materials, flux lattices and superconductors, things of that nature. Leland He has worked with porous materials, and he's done a lot of work with soft matter and polymers. And a scientific associate for the instrument is Cody Pratt. So our scientific associates assist the instrument scientist and the user with things like technical things, administrative work, things of that nature. The GP Sans instrument is really the premier instrument here at Oak Ridge National Laboratory. Its specifications are provided here. So the Q range, you can get down to 007 inverse angstroms fairly comfortably, and the Qmax is about 1 inverse angstrom. We have some lenses that have been tested that get down to 4 times 10 to the minus 4 inverse angstroms, which is pretty respectable. The instrument uses wavelengths from 4 to about 25 angstroms. Obviously, the peak flux is at the shorter wavelengths, but you get your low Q from the higher wavelengths. More often than not, they tend to work around 19 angstroms as their maximum. The GP Sans has the highest flux of any of the SANS instruments at Oak Ridge National Laboratory. It has a large area detector that gives them a dynamic Q range of about 10 to 20. Now, I say measurement times of minutes are possible. That's kind of a cop-out. So in truth, if you have the right kind of sample that scatters extremely well, you can get to sub-second time resolutions on certain things. Minutes are certainly reasonable for many materials. It's a very capable instrument. Importantly, this particular instrument is capable of accommodating the widest variety of sample environments among all the SANs that we have. And it was developed initially with that thought in mind. The scientific program on this instrument includes things like magnetism, materials under pressure, polymers, soft matter. They've done some Rio Sans work. They've done a lot of hard material science in furnaces. And so the instrument from its design is intended to do the most versatile thing. So if you're hoping to do things like time resolved studies that require a large flux, the GP Sans instrument is the one that you would probably want to use. Some of their planned upgrades include things like building out the detector array, things of that nature. So I think it's a really great instrument. I think that the team has done very well working with that. A lot of the scientific focus for many of these instruments grows out of the user community. And I think it's important to be very clear that if you have a sample environment that you would like to use on this instrument or any instrument, you can work with the instrument scientist to confirm that it will fit and to make refinements to do better SANS instruments, and they can help you design sample environments to do your specific kind of science for these beamlines. Next instrument I'm going to talk about is the Biosens. The Biosens is the DOE BER funded SANS instrument. And you can see in the photograph here that it is sitting right next to the GP Sans. These two instruments were developed at the same time. They were just funded through different mechanisms. The team consists of Sai Venkatesh Venki Pingali, who's been with us for a long time. Wellington Leahy is a recent hire to the Biosens instrument. My colleague Volker Urban, who's the section head for the large scale structures section, of which my group is a member, is also an instrument scientist. Clearly, the responsibilities as a manager means that he doesn't necessarily do as much instrument support as the others, but he is engaged. And Luke Haru is a scientific associate. Luke has been at Oak Ridge National Lab for a fairly long time. He actually served as an instrument scientist, as a scientific associate on other instruments up at SNS before moving over to the Biosens. The Biosens is very similar to the GP Sans in terms of capabilities. So the Q minimum is a little bit higher. I don't believe they have lenses at this point in time. Their Qmax is comparable at maximum of 1 inverse angstroms. Their wavelength minimum is 6 angstroms, but they still go out to about 25 angstroms. They also have excellent flux. The Biosens is unique among the SANS instruments at Oak Ridge National Laboratory in that it has 2 detector banks in the tank, which provides it the best dynamic Q range of any of the SANS at ORNL. Much like the GP SANS, because it has excellent flux, measurement times of minutes are certainly possible. Shorter measurement times are also possible. You know, I admit I'm hedging my bets here a little bit on that statement. So the instrument can handle a variety of different kinds of sample environments, but because its mission is centered around biology, because it's funded by the DOE BER, it tends to focus on on a more compact area of science than necessarily you would see on the GP Sans instrument, which is there to serve anybody and everybody. Some of the neat features that they've implemented fairly recently is that they have a sample changing robot now. So this is not simply a linear translation stage with a bunch of samples in a rack. This is a robot that grabs samples out of a place sitting off on the side, puts them in the beam, and it can cycle through far more than you can put in a single rack. They have also developed size exclusion chromatography SANS, which is very common now on synchrotrons. I think this is a great development that this team has implemented finally. Not finally, they've been working on it for a little while, but it's a very good thing. It's very beneficial for that community who does biological solution scattering. So the next instrument is the EEQ Sans at SNS. Unlike the other two instruments that are your traditional pinhole style reactor SANS instruments, the EEQ Sans is a time-of-flight SANS instrument. It is, in appearance, in some sense, very similar to a pinhole SANS at a reactor in that it has a tank with a detector in it that can change distances. It is located on beamline 6 of the SNS, and the team includes Cheng-Woo Do, a Gurgly Nagy, who has recently hired on about 2 years ago at this point, and myself, and Carrie Gao is our scientific associate. Carrie is actually the longest serving member of the EEQ Sans team. Cheng-Woo and I joined in 2011, and Carrie was there for a couple of years before we started. So you will note that the SANS instrument at SNS is not nearly as photogenic as the Biosens or the GP Sans. A lot of that is driven by the use of a lot of additional shielding that is not used at HFIR. So because you're trying to be closer to the source, you've got additional shielding that has to be in place in order to be radiologically safe. The EEQ Sans also has the benefit that we have a lab right next to the hutch. I'll talk a little bit more about that in a bit. So the EEQ Sans, our advertised Q range is 002 to 1.4 inverse angstroms. And that's very easily handled with wavelengths that go from about 2 to 20 angstroms. The bandwidth that we have depends on our detector distance setting and goes anywhere from only 3 angstroms wide when the detector is out at 9 or 10 meters to 4.3 angstroms wide when the detector is 1.3 meters from the sample position. We resolve our wavelengths in this band using time-of-flight techniques. The EEQ Sans does have excellent flux. It's not quite as high as either the GP Sans or the Biosens, but we can certainly do measurements on orders of minutes for the right scattering samples. And yes, if you have a strongly scattering sample, you can probably see changes resolved on tens of seconds, maybe a minute itself. The instrument doesn't quite have as open of a sample environment. That had to do with the fact that the sample area itself is enclosed in steel enclosure for shielding purposes. But we've done a great deal of work trying to free up that space. And at the moment, we can accommodate quite a variety of sample environments. It's not nearly as diverse as the GP Sans one, and the Biosens sample area, should they wish to open it up further than they do now, they've got the room to do it. The EEQ Sans does a bit of RIO-SANS work. So we have a rheometer that we frequently mount inside the sample area. We have your standard sample changers, much like everybody else does. But we also have a recent acquisition of a tensile stage, which is well suited for studying soft materials under stress and strain. And that's been in the user program for not terribly long, certainly less than a year. And I think that's going to be a great addition to the user program. Now I say that, so I mentioned here that the nominal Q range at the high end goes to 1.4 inverse angstroms. in principle, the EEQ Sans actually has wavelengths that are shorter than 2 angstroms. And we have done measurements where we've used 1 angstrom as a minimum wavelength setting. Your Qmax goes higher. Obviously the instrument is not really incredibly well suited to working with those short wavelengths and using such high Q, but it can do it. So if you're trying to do qualitative measurements at higher Q, the instrument is well suited for it. All right, the last SANS instrument at Oak Ridge National Laboratory is the time-of-flight USANS. That's on beamline 1A of the SNS. It's kind of interesting in that it is a time-of-flight Bons-Hart USANS instrument that was originally designed by Michael Agamalian, who many of you know and is no longer with us. The current team consists of Wei-Ren Chen, Yingri Sheng, who is the second instrument scientist on the instrument, as well as the computational instrument scientist for SANS at Oak Ridge National Laboratory. The computational instrument scientists are relatively recent additions to the organization. These are folks who work with staff and users to help them realize both typical support of the computational things like data reduction and such. But I think going forward, this provides an opportunity to have someone who can, in the facility, who can engage with users in more complicated data analyses, simulation, and modeling. Yingri's background is actually in simulations of polymers. And so we're looking forward to getting him engaged with people. Kerry Gao is also the scientific associate on the time-of-flight USANS. The time-of-flight USANS has a Q minimum of about 1 × 10⁻⁵. And the Q max is 0.005 inverse angstroms, which means that it can overlap with all 3 of the SANS instruments at Oak Ridge National Laboratory, which is really useful. It means that someone can do a measurement on the USANS, do a measurement on one of the other SANS instruments, piece the data together and analyze it all at one time. And at the moment, someone who proposes to use the time-of-flight USANS can also just tick a little box in the proposal system and say, I would also like SANS. And we've been generally accommodating those measurements on the EEQ Sans. And that seems to be a really popular way that people can get SANS and USANS. So the mechanism is limited to getting SANS data on the samples that you measured with the USANS. And we usually can do that within about a day. The instrument uses 4 different wavelengths that we actually resolve with time of flight. So these are just the harmonics that are coming off of the crystals. Measurement times are on the order of 8 to 12 hours per sample, which we would love to have it be faster than that, but we don't get that from the source. So it's got a really nice clean background, but it is not a high throughput instrument. But we're looking forward to this instrument's contribution to the user program here at Ornell. It's actually the newest instrument at SNS, not counting the one that's currently under construction. And it went into the user program in 2016, or it completed construction in 2016. It actually has the ability to accommodate a fairly wide variety of sample environments. Probably the biggest challenge you have is that the instrument itself is not terribly large. So you can see the entire instrument here mostly, and you do have some limitations, but things like furnaces, cryostats, the rheometer still fit in that space, and you can use them for doing your experiments. All right. So we do have a fairly wide variety of sample environments that are available that you can use on the SANS instruments and on the time-of-flight USANS. The Neutron Scattering Division centrally manages quite a few different kinds of sample environments. So magnets, cryostats, furnaces, things that are fairly large pieces of equipment, those are all centrally managed, and you can see them here at neutrons.ornl.gov/sample. The SANS instruments also have quite a few sample environments that are directly managed by the beamline teams. You can get some information on the various beamline pages shown here. It's probably not comprehensive. My advice is if you have questions about whether or not we have something, feel free to reach out to the instrument staff directly. We're happy to talk to you. And I do want to reiterate that any of these instruments can accommodate your user-supplied sample environments as long as they'll fit and as long as the safety people say it's okay to use them. So if you bring something in, your sample environment will be subjected to the standard safety reviews that everybody goes through. That includes an electrical safety review for user-developed equipment that don't have UL listing or similar listings. But we're happy to work with you. We'd love to hear your ideas, and we'd love to have you here to do your own interesting science. So I also want to bring to everybody's attention the laboratories that are available at SNS and HFIR. So the SNS actually has a fairly comprehensive laboratory space that's available to users. Quite a few of them are centrally managed again, and we serve all the beamlines with them. We have considerable amount of equipment that's available for characterizing your samples, for preparing your samples. As I mentioned, the Center for Structural and Molecular Biology operates the biodeuteration laboratory that also includes materials characterization laboratories that go along with the rest of their effort. So spectroscopies, optical and IR, et cetera, those are available. We do also have some space for longer term work. So if what you're working on really requires you to spend considerable amount of time preparing your sample and is best done on site in preparation for your neutron experiment, we can work with you. We have some X-ray scattering instruments that are available to users. So powder crystallography, macromolecular crystallography, small angle X-ray scattering for biology, X-ray reflectometry. The Center for Nanophase Materials Sciences also has instruments that you can request. So if you have an approved proposal for neutron scattering experiments, you can request access to characterization facilities in the Center for Nanophase Materials Sciences. And if your experiment is up in SNS, you just go down the hall and you're in CNMS right away. ORNL is, much like all the other DOE laboratories, a very large organization, and in the event that we don't have the kind of characterization that you need to do on site in preparation for your experiment, we might be able to find somebody who can help you out. Maybe. They may be in a different part of the campus entirely, but we might be able to help out. There are also laboratories that are really close to the beam line. So in the case of the EEQ Sans instrument, our hutch is right next to the laboratory at the beam line called the Southside User Lab. Very convenient for people who are working on SANS, who want to do time resolved things where they have to mix something really quick and then run it into the instrument. It is a fully equipped lab. We've got a HEPA fume hood for working with nanomaterials. There's a glove box for working with other materials, fridges for storage of stuff. And we can bring equipment over from the main laboratories to the EEQ Sans lab so that you could do characterizations right there at the beam line and do your work. Now, this laboratory is available to anybody who's doing any experiments in the SNS, but this one is, like I said, really convenient for the EEQ Sans instrument. It was actually part of the construction project for the beam line. Similarly, at the HFIR, there are some very nice laboratory spaces available for users to work with their materials. Again, it is a fully outfitted laboratory, and you can request access to any of these laboratory spaces during the proposal process or during the confirmation of your proposal as you prepare for your experiment. And if we don't have the equipment that you need, you can probably find a way to get it to you. We also have some chemicals that are available, so you don't have to drag along everything if you don't want to. The CSMB does have a small lab in the cold guide hall that's right next to the main user laboratory space shown here. And I do want to reiterate, we are right next door to the Center for Nanophase Materials Sciences. CNMS is a DOE BES funded user facility. And when you prepare a proposal for the CNMS, you can include a neutron appendix that says, after I do my work in the CNMS, I need to do neutron scattering with these samples. And the link is shown here. So if you want to do some SANS experiments at Oak Ridge National Laboratory, we would be happy to have you. Just visit neutrons.ornl.gov for further information. And with that, I thank you for your time. And I do want to share information about the potentials, so the schedules for the facility. So let me stop sharing this. I will share a different screen. Here we are. So I'm going to share this one, share that. No, not that. Here we go. Okay, so as I mentioned, we are undergoing some upgrades. So the SNS is going through the proton power upgrade, which is a significant upgrade to our accelerator. And the High Flux Isotope Reactor is going to go through some upgrades as part of the HFIR beryllium reflector replacement. And so while we are happy to have you come here, I will let you know up front that Oak Ridge National Laboratory is going to have some significant outages during these upgrade processes shown here. So SNS, in preparation for the proton power upgrade, is going to have some extended outages in August, and a much longer one starting in February of 2023, where we won't be back online, but we'll be coming back at higher power in December of 2023. Then there's a slightly longer outage in 24 before we're continuing our march towards full 2 megawatt operations. As I said, we're right now at 1.4 megawatts. We go to 2 megawatts, we get better flux on all the beam lines out here. Also shown here is what's going on at HFIR. So the HFIR beryllium reflector replacement is a necessary maintenance activity that's going on at HFIR. They must change out the beryllium reflector after a certain number of cycles. So what you're seeing here is you're seeing these increasingly long outages. That's to ensure that we have some productivity, some neutron scattering available at Oak Ridge National Laboratory while the SNS is undergoing its upgrades and in preparation for the HFIR upgrades. So the HFIR project right now, according to this schedule, which is available on the neutrons.ornl.gov website, you start to have these extended outages starting in 24, with the longer ones being in 25 and into 26 before we get back into typical operations. So something to keep in mind as you're thinking about potentially doing experiments at SNS and HFIR. It's not that we're going away, but that there will be some pressure on our time going forward. And with that, I will end, and I will be happy to take any questions that you have.